Hi दोस्तों, welcome to Toral Education and today we are taking chapter number 1 नंबर सिस्टम। नंबर सिस्टम में दोस्तों आप देख सकते हैं कि अलग अलग टाइप के नंबर्स हैं और ये सारे जो नंबर्स हैं उसके अंदर फर्स्ट है नेचुरल नंबर। नेचुरल नंबर्स, all counting numbers are natural numbers. For example 1, 2, 3, 4, 5 ये सारे नेचुरल नंबर्स हैं। दूसरा है होल नंबर्स। होल नंबर्स किसको कहते हैं? नंबर्स बिगिनिंग फ्रॉम जीरो इंक्लूडिंग ऑल नेचुरल नंबर्स आर नोन एज होल नंबर्स। नंबर्स बिगिनिंग जो शुरुआत होती है जीरो से और 1 से लेकर के इनफाइनिट तक जाते हैं उसको हम बोलते हैं होल नंबर। सो सारे नेचुरल नंबर होल नंबर्स में आ गए। Natural numbers are whole numbers, but whole numbers are not natural numbers. Remember this. Then comes integers. All negative and positive numbers are integers. Negative and positive whole numbers. We can say negative and positive numbers, not fractions. They are integers. Minus infinite to plus infinite, including 0. That is -3, -2, -1, 0, 1, 2, 3, 4, 5 up to infinite. They are integers, right? Then comes rational numbers. A rational number, the number which can be shown in the form of P upon Q. P upon Q, that means in the form of fraction. In the form of fraction. P upon Q, where P is a whole number and Q is a natural number. Natural number, that means Q should not be negative. 1 to infinite, and P is whole number, that means 0 to negative integers to positive integers. This is known as a rational number. When the reduced form of fraction that means P upon Q is same, then they are known as equivalent fraction. Equivalent, that means they are equal in the reduced form. Look at here. 1 upon 2, 2 upon 4. If we cut this fraction, 2 2s are 4, then it comes 1 upon 2. If we cut this fraction, 3 upon 6, 3 2s are 6, that is 1 upon 2. 4 upon 8, that is 1 upon 2. So when the fraction in the form of reduce, it comes same, then they are rational equivalent fractions. There are infinitely many equivalent fractions of one fraction. Infinitely many. आप कितने भी कर सकते हैं equivalent fractions. When you multiply or divide the numerator and divide with the same numbers, you will get equivalent fractions. Look, in this example, 1 upon 2, we have multiplied both the numbers by 2. 1 2s are 2, 2 2s are 4. Then we have multiplied by 3. 3 1s are 3 and 3 2s are 6. Right? Then we multiplied 4. 1 4s are 4 and 2 4s are 8. Right? Equal numbers are multiplied to the fraction, then we get equivalent fractions. There are infinitely many rational numbers between two rational numbers. P upon Q form is the rational form of the number. Then there are so many numbers between both, infinitely many numbers. Between numbers can be found out by r plus s upon 2. R plus s upon 2, that means r and s are the two rational numbers. P upon q, 1 upon 2 and 3 upon 4, these two are rational numbers. Then 1 upon 2 is called r and 3 upon 4 is called s. These two numbers. This is formula to find out rational number between two rational numbers. We can also find the rational numbers between two rational numbers by taking LCM. You will see in the exercise by taking LCM. Look at the exercise 1.1. 1.1. So here are some sentences. Is 0 a rational number? Can you write it in the form of P upon Q, where P and Q are integers and Q is not equals to 0? Yes, answer is yes. Here I have given answers only. You should see the questions in exercise, that means in the textbook. Yes, 0 is a rational number. It can be written as 0 upon 1, 0 upon 2, 0 upon 3, etc. as P upon Q. Right? Then second question. Find 6 rational numbers between 3 and 4. 6 rational numbers between 3 and 4. Then let's take r plus s upon 2. R, that means 3, s, that means 4, upon 2, that is 7 upon 2. Right? 3 plus 4, 7 upon 2. Then it will be s. Look, 3 is r and 7 upon 2, this one is s. 3 plus 7 upon 2, that means we have taken 2 as LCM. 2 3s are 6. 6 plus 7 upon 4, because LCM goes down. 6 plus 7 upon 4, that means 13 upon 4. Then I have taken 4 plus 7 upon 2. We want to find out 6 rational numbers. This is a long process. I will show you short process also. Short method. Right? In this way, 4 plus 7 upon 2, 2 4s are 8, 8 plus 7 upon 4 is equals to 15 upon 4. Here 15 upon 4 and 7 upon 2. Right? 7 upon 2. Upon 2. 4 is LCM. Then here will be 14. 15 plus 14 and 4 goes down. That is 4 2s are 8. 15 plus 14 upon 8, that means 29 upon 8. Similarly, 13 upon 4 plus 7 upon 2 we have taken upon 2, that is 13 plus 14, because 4 is LCM. 4 is LCM. 4 here, 2 here, that means it will be 7 will be multiplied by 2 only. 7 2s are 14. Sorry. 13 plus 14 upon 8. So 27 by 8. R plus S, that means 27 upon 8 plus 7 upon 2. We have to take two numbers, R and S upon 2. We will find out infinitely many numbers between two rational numbers. So we have got here 15 upon 16. So these are our numbers. Sorry. Our numbers are 13 upon 4, 27 upon 8, 55 upon 16, 7 upon 2, 29 upon 8, 15 upon 4. These all numbers are between 3 upon 4, 3 and 4. 3 and 4. These all numbers. So these numbers may be different because there are infinitely many numbers between two rational numbers. Right? If you match the answer given in the textbook or given in any other reference book, you may find different numbers because there are infinitely many numbers. Here question number 3. Find 5 rational numbers between 3 upon 5 and 4 upon 5. 3 upon 5 and 4 upon 5. Here I have taken LCM. LCM is 5. Right? We multiply both the fractions by 6. That means if the numerator P is consecutive number, right? 3 and 4 are consecutive. Then by taking LCM, we will have to take one number more. That means if we want to find out 5 rational numbers, then we will take 6. If we want to find out 6 rational numbers, we will take 7. Right? So 3 upon 5 into 6 upon 6, that is 18 upon 30. 4 upon 5 into 6 upon 6, both the numbers are multiplied by the same numbers, 24 upon 30. Right? So between 18 upon 30 and 24 upon 30, we get these numbers 19 upon 30, 20 upon 30, 21 upon 30, 22 upon 30 and 23 upon 30. These are 5 numbers between 3 upon 5 and 4 upon 5 by taking LCM. The question number 2 can also be found by taking LCM. Question number 4. State whether the following statements are true or false. Right? Give reason. First, every rational number is a whole number. Every natural number is a whole number. I have given the statement in the beginning when I was defining the numbers. Every natural number is a whole number. This statement is true because all natural numbers are included in the whole numbers. Whole numbers begins from 0 and natural number begins from 1. So 0, 1, 2, 3 and up to infinite, and 1, 2, 3 up to infinite. All natural numbers are whole numbers. Second question, every integer is a whole number. Every integer that means negative and positive. But whole numbers are not negative. Right? Every integer is a whole number. This statement is false because integers contain negative numbers also. But whole numbers begin from 0. 0 is neither negative nor positive. 0 is neither negative nor positive. So it begins from 0, 0, 1, 2, 3, 4, 5. And integers begin from -3, -2, -1. So whole numbers are not integers. Integers are not whole number. Whole numbers are integers, but integers are not whole numbers. Every rational number is a whole number. Every rational number that means in the form of P upon Q. This statement is also false because rational numbers may be negative, 0 or positive, but whole numbers never be negative. Whole numbers never be negative. Rational numbers may be negative, positive or 0. Now we will have irrational numbers. Right? Irrational numbers. What are these? Irrational numbers. Numbers which are not rational, which cannot be shown in the form of P upon Q. That means in the form of fraction. They are irrational numbers. The numbers which cannot be shown in the form of P upon Q are known as irrational numbers, such as root 2, root 5. All numbers which cannot be divisible by any other numbers, that are root 2, root 5, pi, 3.01, 001, 0001, etc. are rational numbers. They cannot be shown in the form of P upon Q. Right? Then real numbers. All rational and irrational numbers are real numbers. So real number is the final set of numbers. We can say rational and irrational are included in real numbers. Right? Remember that every real number is represented by a unique point on the number line. We can draw a number line, and on this number line we can represent a unique point as rational number, as real number. Also, every point on the number line represents a unique real number. That means we can represent every real number on the number line. Right? We can do it. Here, in 1870s, two German mathematicians, Cantor and Dedekind, showed that corresponding to every real number, there is a point on the real number line, and corresponding to every point on the number line, there exists a unique real number. These two mathematicians have given this statement. Remember the name? Cantor and Dedekind. Right? Here we have exercise 1.2. Exercise 1.2. This is a small exercise, so I have taken it together with 1.1. 1.1 was also small, little, so we can do it. So first is state whether the following statements are true or false. Justify your answer. So first is every rational number is a real number. Every irrational number is a real number. It is true. Irrational, right? Here I have made a mistake. Not rational but irrational. It is true because rational and irrational numbers are real numbers. They are included in real numbers. So every number is a real number, we can say. Either it is rational or irrational. Second, every point on the number line is of the form of root m, where m is a natural number. Every point on the number line is of the form of root m. Root m. Maybe some points are not root of any number. It is false because there is a real number corresponding to every point on the number line, not only natural numbers. Right? Question number 3. Every real number is an irrational number. Every real number. It is also false because real numbers include both rational and irrational numbers, not only irrational numbers. So rational and irrationals are included in real numbers. Here friends, question number 2. Question number 2 is are the square roots of all positive integers irrational? Question is, are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. Here I have given answer no. Every positive number, square root of every positive number is not an irrational number, right? The square root of all positive integers are not irrational. Here are some examples. Square root of root 1. Square root of 1 is 1, which is rational. It's not irrational. Square root of 2 is square root of 2, but it is irrational. Root 3, which is irrational. But root 4, we get 2, which is rational. So this statement is false. Here is the real number which is irrational, and we have to show it on the number line. Root 5 on the number line. Look at the number line. Look at the number line. Here is number line from 0 to 1, 2, 3, 4, 5 up to infinite. Right? Here 0 means O, point O. I have shown it on this number line. Look at how. First take a number line. Remember the steps. First take a number line. We will have Pythagoras theorem in our mind. So 0 to 1, that is 1 unit. Take 1 unit perpendicular from 1. 1 unit perpendicular from 1. Perpendicular, that means at 90 degree, at right angle. Then construct a line which is called hypotenuse. Right? Pythagoras theorem says the square of hypotenuse is equals to the square of the other two sides which form the right angle. So here 1, here 1. Square of 1 is 1, square of 1 is 1. 1 plus 1, that is 2. Then we take square root of 2. That means it is the square root of 2. This line is square root of 2. Again take 1 perpendicular to this root 2. Root 2 plus 1, that is root 3. Root 3 plus 1, that is root 4. This one is root 4. And root 4 plus 1, that is root 5. We have taken this number, this line is root 5. And if we mark an arc taking 0 as center, we get this line, this curve after 2. Because this one is root 4, 2 is root 4, 2 is root 4, and this point is root 5. Here it is root 5. Okay, so we have shown this on the number line root 5. Now friends, to locate root m number on the number line, the following steps are to be followed. Here are steps. Draw a number line and mark numbers 0, 1, 2, 3, 4 at equal distance. Right? Take 0 as origin and from 1 draw a perpendicular of length 1 unit. Perpendicular of length 1 unit. We have taken here perpendicular of length 1 unit. Right? Draw hypotenuse, which is root 2. I told you according to Pythagoras theorem. Here is hypotenuse. This one is root 2. This is root 2. Similarly, repeat the action and complete your number line by locating root 2, root 3, root 4, root 5, etc. But we have an alternate method to show the numbers on number line. Look, root 5. Root 5, that means root 4 plus 1. 4 plus 1 is 5. Take here perfect squares only. 4 is a perfect square, 1 is a perfect square. Don't take 2 plus 3, right? Right? This is also 5. But don't take it. Only perfect square. 4 plus 1. 4 means square root of 2, square of 2, and 1 means square of 1. So first of all, we have to take here unit 2. Unit 2. Look. Unit 1, unit 2. Then here is 1. So we have to take perpendicular 1 unit. Then join 0 to this point. And taking O as center, mark an arc on the number line which show you root 5 on the number line. Right? We can show any irrational number on this number line by this method. So friends, Here question number 4. Question number 4 is a classroom activity. Do it by yourself if you can. Right? Question number 4 is a classroom activity. You can do it by yourself. So friends, we have completed one video, exercise 1.1, 1.2. We will take exercise 1.3 on this in the other video. So friends, till then, goodbye and thank you for watching the video. Thank you very much.